A fish was lying beneath a pile of sharks and rays on a South African dock when someone noticed that its fins did not look like fins at all. They looked like limbs. It was the 22nd of December, 1938. The fish was about 1.5 meters long, which is about 4.9 feet, covered in blue-gray scales that looked more like armor than skin. It was still alive when it came ashore. Science already knew this animal, or at least it thought it did. Its fossils had been studied for more than a century. It had a place on the evolutionary tree. It had an extinction date of 65 million years ago. Every textbook, every museum display, and every scientific reference agreed that it had vanished alongside the last non-avian dinosaurs. It had never vanished at all. The woman who found it had no formal scientific training, no refrigeration, and almost no one willing to believe what she had discovered. She spent the next 2 days fighting to preserve a specimen that was disappearing before her eyes, setting in motion an obsession that would consume one of the world's leading fish scientists for the next 14 years. When he finally stood in front of it, he later wrote that the sight struck him like a white-hot blast. Then, nearly 6 decades later, a honeymoon trip to a fish market revealed something even more astonishing. There was not one surviving population. There were two, separated by almost 10,000 kilometers, which is about 6,200 miles, and living in different parts of the Indian Ocean. In this story, we're following one of the most extraordinary scientific discoveries ever made, from a forgotten dockside catch to an animal that forced the world to rethink extinction itself. If this is the kind of journey you enjoy, a quick like or subscribe goes a long way. It helps us keep bringing these remarkable stories to curious minds like yours. Now, let's begin. Long before forests cast shadows across continents, before reptiles traced their first paths through ancient landscapes, and long before the age of dinosaurs began, another lineage had already entered Earth's story. Its earliest known fossils reach back roughly 420 million years, into the Devonian period, when much of the world was covered by warm, shallow seas that nurtured some of the earliest complex vertebrate life. Across those waters, the ancestors of the coelacanth were already swimming through a planet that would transform beyond recognition. Over immense spans of geological time, this lineage flourished. Fossil discoveries have revealed roughly 90 distinct species, occupying an extraordinary range of habitats that stretched across ancient oceans, coastal waters, rivers, and freshwater lakes. Their remains have been uncovered on continents now separated by vast distances, preserving evidence of a group that once achieved a worldwide distribution. Each fossil became another page in a history written across changing shorelines, drifting continents, and oceans that opened and closed over countless ages. The coelacanth belongs to the ancient lineage known as lobe-finned fishes, formerly called Sarcopterygiae. Unlike the ray-finned fishes that dominate nearly every modern river, reef, and open sea, these animals carried paired fins built upon fleshy muscular lobes supported by internal bones. Within that ancient branch of vertebrate life rested an evolutionary design that would eventually stand near one of the greatest turning points in natural history. Its unusual name reaches back to the Greek language, meaning hollow spine, inspired by the distinctive hollow structures within the fin rays observed in fossil specimens. Even before a living individual was ever seen, generations of paleontologists recognized those characteristic features embedded in stone. The fossils were so distinctive that the animal seemed firmly anchored within Earth's distant past, cataloged with confidence among creatures belonging only to vanished worlds. Although the coelacanth is not the closest living relative of land vertebrates, That place belongs to the lungfish. It occupies a neighboring branch on the same remarkable family tree, close to the point where ancient lineage divided. One branch eventually gave rise to animals that would leave the water behind, while another continued its existence beneath the surface. That position grants the coelacanth a rare importance, preserving characteristics that illuminate one of evolution's greatest transitions without standing directly upon the path itself. Then the fossil story reached an unexpected ending. By the close of the Cretaceous period, approximately 66 million years ago, the record simply stopped. Younger rock layers yielded no confirmed remains. The disappearance aligned with the same global catastrophe that ended the reign of the non-avian dinosaurs, reinforcing what appeared to be an obvious conclusion. The lineage had finally vanished alongside countless others swept away during that ancient upheaval. For more than a century, paleontologists accepted that conclusion with complete confidence. Museums displayed beautifully reconstructed fossils beneath labels identifying the coelacanth as extinct. Scientific textbooks repeated the same verdict from one generation to the next. Classifications, research papers, and educational collections all agreed with remarkable certainty. The absence of younger fossils appeared absolute, leaving no visible thread connecting those ancient skeletons to the living seas of the modern world. That confidence rested undisturbed until late in the year 2938, when an unexpected telephone call from a dockyard in South Africa carried news that seemed impossible. In a single ordinary moment, an assumption that had endured across decades of careful scientific work began to unravel, not because the fossil record had changed, but because the living ocean still held a chapter that stone had never revealed. The history preserved beneath layers of ancient stone is rarely continuous. It resembles scattered pages from an immense chronicle, with long stretches carried away by erosion, buried beneath younger landscapes, or never written into rock at all. Yet across those fragmented pages, the coelacanth appeared again and again, enduring through chapters that erased countless other forms of life. Its fossils passed through the late Devonian extinction, approximately 375 million years ago, when nearly 75% of Earth's known species disappeared. Ancient seas changed profoundly as ecosystems collapsed and recovered across immense spans of time. Entire communities vanished from the record, while others emerged to occupy newly emptied waters. The coelacanth lineage remained present on both sides of that boundary, continuing its unbroken passage through a world that had become almost unrecognizable. Millions of years later came an even greater catastrophe. Around 252 million years ago, the Permian-Triassic extinction reshaped life more completely than any other known event in Earth's history. Approximately 96% of marine species disappeared, along with vast numbers of organisms living on land. Oceans became hostile to many of the creatures that had flourished for millions of years. Food webs collapsed, habitats vanished, and evolutionary history narrowed to the comparatively few lineages capable of enduring the transformation. Once again, coelacanth fossils appear before the devastation and continue afterward, their ancestry bending through the crisis without breaking. The pattern repeated during the Triassic-Jurassic extinction, approximately 201 million years ago. Roughly 80% of known species disappeared as climates shifted and ecosystems reorganized across the planet. The disappearance of so many competitors created ecological opportunities that allowed dinosaurs to become the dominant large animals across the continents. Beneath the surface of ancient seas, however, the coelacanth lineage continued its measured existence, leaving behind fossils that marked continuity where countless neighboring branches of life had ended forever. Viewed together, these successive appearances reveal something remarkable. Each extinction boundary forms a geological line dividing one version of Earth from another. On both sides of those boundaries, the distinctive anatomy of the coelacanth remained recognizable. Continents drifted apart, mountain ranges rose and eroded, coastlines advanced and retreated, yet the lineage itself persisted through changes that reshaped nearly every ecosystem on the planet. Then the sequence ended. At the close of the Cretaceous Paleogene extinction, approximately 66 million years ago, the fossil record fell completely still. The asteroid impact that transformed Earth's climate and ended the age of the non-avian dinosaurs also marked the final known appearance of coelacanth fossils. Every younger geological formation examined across subsequent generations failed to produce another confirmed specimen. Layer after layer recorded changing oceans filled with evolving marine life, yet the familiar hollow fin rays and unmistakable skeletal features never returned. That absence carried extraordinary weight because it stretched across an interval longer than human civilization, longer than the rise of mammals, longer even than the time separating the modern world from the extinction of the dinosaurs themselves. For 66 million years, the coelacanth existed only as an inhabitant of stone, its story apparently complete. Geologists examined marine sediment recovered from ocean basins around the world, reading each layer as another page in Earth's long memory. The intervals where living coelacanths should have left evidence appeared empty. Their disappearance seemed complete enough to become certainty, accepted not through assumption, but through repeated observation gathered over generations of careful study. Looking backward, that span is often described as a gap, yet from the perspective of the fossil record itself, it was something even deeper. It was an uninterrupted absence, extending across millions upon millions of years, leaving behind no visible trace that the lineage had continued beyond the age when science believed its final chapter had already been written. Some discoveries begin with elaborate expeditions planned over many years. Others arrive during an ordinary working day, carried ashore among the routine catch of local fishermen. The turning point in the story of the coelacanth belonged to the second kind, and at its center stood a woman whose greatest qualification was an unwavering habit of paying attention. Marjorie Courtenay Latimer was born in East London, South Africa, in the year 1907. Her father worked as a railway station master, and from childhood she developed a lasting fascination with shells, birds, plants, and the countless forms of life surrounding the coastline. Although she never received formal scientific training through a university, her determination and lifelong devotion to natural history gradually earned her a place as curator of the East London Museum. It was an appointment built less upon credentials than persistence, careful observation, and a willingness to learn directly from the natural world itself. She cultivated friendships with fishermen working the nearby coast, understanding that museum collections often grew not only through organized fieldwork, but also through unexpected encounters. Among those contacts was fishing captain Hendrik Goosen, master of the trawler named Nerine. They shared a simple arrangement. Whenever his crew hauled aboard something unusual, he would send word to the museum, knowing that Marjorie would want to examine it before it disappeared into markets or processing facilities. As the year 1938 drew toward its close, preparations for the holiday season occupied much of the museum's attention. On the morning of December 22nd, Marjorie was already busy with ordinary responsibilities and briefly considered remaining where she was instead of visiting the harbor. Later, when recalling the events of that day, she explained the decision with remarkable simplicity. she felt she should go. The trawler had returned after working near the mouth of the Chalumna River, unloading sharks, rays, and many familiar species gathered from the coastal waters. Moving carefully among the catch, Marjorie searched for anything worth preserving. Then her attention settled upon something almost hidden beneath the larger bodies surrounding it. The fish possessed a form unlike anything she had encountered before. It measured nearly 1.5 meters in length, which is about 4.9 feet. Its body carried a pale blue-purple coloration, dusted with delicate white speckles that seemed almost painted across remarkably hard scales. Most striking of all were its paired fins. They projected outward on thick, muscular lobes instead of the slender supports familiar in ordinary fishes. Rather than suggesting fins alone, they carried the unmistakable impression of limbs suspended beneath the body. The animal had still been alive when the fishing nets brought it aboard. By the time Marjorie reached the docks, only the final signs of life remained. Even so, the appearance of the creature held her attention with complete concentration. She searched through her memory, comparing every feature against the illustrations and descriptions she had studied over years of museum work. Nothing corresponded. No handbook resting on the museum shelves described a fish that looked remotely like the one before her. Recognizing that memory alone might not preserve such extraordinary details, she began making careful sketches. She measured proportions, recorded the placement of every fin, traced the contours of the head, and noted the arrangement of the scales as accurately as circumstances allowed. Without realizing it, she was creating the first scientific record of a living animal believed absent from the world for tens of millions of years. The pages she filled that day would become far more than field notes. They preserved the appearance of a creature that seemed to exist outside the accepted history, captured first not through certainty, but through careful observation and the refusal to overlook what others might have passed by. Recognition alone could not preserve the remarkable creature resting before Marjorie Courtenay-Latimer. The first challenge was far more immediate. Every passing hour carried away details that no future discovery could ever restore, and the coastal town offered few ways to protect such an enormous specimen from the warmth of a South African summer. The fish measured nearly 1.5 meters, which is about 4.9 feet, making it far too large for ordinary museum storage. East London possessed no refrigerated facility capable of accepting an animal of its size on such short notice. Ice was scarce, specialized preservation equipment was unavailable, and decomposition had already begun its steady work. The extraordinary importance of the specimen remained known only to one museum curator whose conviction rested entirely upon observation rather than proof. Marjorie searched for any solution within reach. She appealed to a taxi driver in hopes of transporting the fish somewhere suitable. She contacted a local mortuary, believing its cooling rooms might provide temporary refuge. She approached refrigeration facilities wherever one could be found. Each possibility ended the same way. Some locations lacked enough space. Others declined altogether. Time continued moving, while every unsuccessful attempt narrowed the chances of preserving the specimen in its original condition. Eventually, she persuaded a local taxidermist to accept the fish. It was not an ideal scientific solution, but it was the only practical choice remaining. By then, the natural processes acting within the body had advanced too far to stop. Soft tissues had begun breaking down beyond recovery, taking with them information that later generations of researchers would have treasured above almost everything else. The greatest loss lay hidden beneath the skin. The stomach could no longer reveal what the animal had recently eaten. the intestines offered no opportunity to examine its digestive system intact. The reproductive organs vanished before anyone could determine its maturity or breeding condition. Other delicate tissues, carrying clues to physiology and internal anatomy, disappeared before a trained specialist ever laid eyes upon them. Those missing structures represented knowledge that could never be recreated from memory, sketches, or fossilized bones. Even so, Marjorie refused to let the discovery disappear entirely. She carefully prepared a detailed letter addressed to James Leonard Brierly Smith at Rhodes University, the ichthyologist whose expertise she trusted above anyone else. Along with her written description, she enclosed the sketches made at the docks, recording proportions and anatomical features with as much precision as circumstances had allowed. Fate introduced yet another delay. Smith was away on holiday when the letter arrived, leaving it unopened while precious days slipped by. The specimen remained in East London, preserved as well as circumstances permitted, waiting for someone who still had no idea that an impossible message rested among his correspondence. When Smith finally read Marjorie's account, recognition came almost instantly. Years later, he described the experience by writing that a bomb seemed to explode in his brain. The anatomical details contained within her careful observations pointed unmistakably toward a coelacanth, an animal that every scientific reference insisted had vanished tens of millions of years earlier. His reply traveled with urgency. He sent a telegram instructing that the skeleton and gills be preserved above all else. By the time those words reached East London, the internal organs had already been lost beyond recovery. Yet the skin remained, the scales endured. Most importantly, the skeleton survived intact, carrying enough evidence to establish the identity of the impossible fish beyond reasonable doubt. What endured from those difficult days was not perfection, but persistence, a decision to visit the docks, a determination to keep searching for help despite repeated refusals, and the patience to document every visible detail, transformed an ordinary museum curator into the guardian of one of the most consequential biological discoveries of the modern age. Nearly 2 months passed before James Leonard Brierly Smith finally stood in the same room as the preserved fish. During those weeks, he had lived with certainty, formed through sketches, written descriptions, and photographs, assembling the evidence piece by piece until there seemed little room for doubt. The mind had already reached its conclusion. The eyes, however, still had their own journey to make. Smith arrived in East London on February 16th in the year 1939. The specimen had already been mounted by the taxidermist, preserving the broad outline of the animal even though its most delicate tissues had long since disappeared. Everything he had studied from a distance suggested that the impossible had become real. Still, no photograph could fully convey the proportions, the texture of the scales, or the unfamiliar architecture of the fins resting beneath the body. He approached with the confidence of a scientist prepared by years of experience, yet the moment unfolded very differently from what reason alone had promised. Later, he described the encounter in deeply personal terms. Although he believed he was ready, that first sight struck him like a white-hot blast and left him feeling shaky and strange. The words came not from someone easily carried away by excitement, but from a man whose professional life had been devoted to the study of fishes. For a long interval, he simply remained before the specimen. Conversation gave way to observation. Every feature confirmed what logic had already accepted, while simultaneously resisting belief. The thick scales, the distinctive lobed fins, the proportions of the skull, and the unmistakable anatomical details matched creatures previously known only from ancient stone. Fossils had prepared him for recognition. Reality demanded something different, asking him to reconcile millions of years of accepted history with the evidence standing only a few steps away. The scientific consequences became clear almost immediately. On March 18th, in the year 1939, Smith formally described the animal in a letter published by the journal called Nature. He assigned the name Latimeria chalumnae. The genus honored Marjorie Courtenay Latimer, whose careful attention had prevented the specimen from disappearing unnoticed. The species name honored the Chalumna River, near whose mouth the fish had been caught. Together, those names permanently joined both the discoverer and the place of discovery to one of the most remarkable animals ever identified. Even within the normally restrained language of scientific publication, Smith described the discovery as most important and surprising. Such wording carried unusual weight. Scientific papers often favored careful moderation, especially when announcing extraordinary claims. Yet the evidence before him allowed little room for cautious understatement. A lineage believed absent since the Cretaceous-Paleogene extinction had entered the modern world without changing its identity. News traveled rapidly beyond scientific circles. Newspapers across many countries reported the rediscovery, with some describing it as one of the greatest scientific discoveries of the 20th century. Museums, universities, and natural history collections suddenly found themselves discussing an animal that had crossed from the fossil record into living memory. Decades later, South Africa commemorated the anniversary of the discovery with a block of postage stamps, recognizing how profoundly one unexpected catch had altered humanity's understanding of life beneath the sea. For Smith, however, celebration never erased a lingering absence. The preserved skeleton, skin, scales, and external anatomy had answered one astonishing question, yet the missing internal organs continued to trouble him. Without them, many details of the creature's biology remained beyond reach. Even as the scientific world welcomed the return of the coelacanth, his attention settled upon what had been lost during those first difficult days, and that missing knowledge became the steady purpose guiding the years that followed. For many scientists, confirming the existence of a remarkable animal would have marked the end of a long pursuit. For James Leonard Brierly Smith, it became the beginning of another, far more demanding one. The preserved specimen had transformed certainty into reality, yet the missing anatomy hidden within its lost organs left the most intimate chapters of the animal's biology forever unread. Smith became convinced that only a freshly caught coelacanth could answer those lingering questions. He needed an individual whose internal structures remained intact, allowing careful study before natural decay erased them once again. Every year that passed without such a specimen prolonged an unusual scientific frustration. The world's rarest fish had returned, yet many of its greatest biological secrets remained inaccessible. Determined to find another, Smith organized a campaign that stretched across much of the western Indian Ocean. Thousands of illustrated leaflets were printed and distributed along the coastlines of Mozambique, Madagascar, Tanzania, and the Comoro Islands. They appeared in fishing villages, harbors, government offices, and ports where unusual catches occasionally surfaced. To reach as many communities as possible, the notices were prepared in English, French, and Portuguese, languages commonly spoken throughout the region. Each leaflet carried a detailed illustration of the extraordinary fish, along with a simple promise written in Smith's own words. Anyone providing reliable information leading to a fresh specimen would receive a generous reward. The appeal depended not upon laboratories or research vessels, but upon fishermen whose daily work brought them into waters that scientists themselves rarely visited. Then came a remarkable stretch of waiting. Season followed season as fishing boats continued their ordinary routines across immense reaches of ocean. Nets rose from deep water carrying familiar catches, while the image on Smith's leaflets slowly became another face remembered by coastal communities. Reports arrived from time to time, yet none proved genuine. Month after month unfolded into years, and the extraordinary fish remained absent from scientific reach. The long silence gradually reshaped Smith's thinking. The first specimen no longer appeared to him as an isolated wanderer carried accidentally toward the South African coast. Instead, he began imagining a stable population living far beyond ordinary observation, somewhere within the deeper waters of the western Indian Ocean. If one individual had reached fishing nets, others almost certainly remained where the species had survived unnoticed across countless generations. His attention settled increasingly upon the Comoro Islands, a volcanic archipelago lying between Madagascar and the eastern coast of Africa. The steep underwater slopes surrounding those islands descended rapidly into great depths, creating habitats unlike the broad continental shelves found elsewhere. To Smith, those volcanic waters seemed capable of sheltering exactly the kind of elusive population he had begun to envision. Years of patience finally gave way to a single unexpected message. During December of the year 1952, a telegram arrived from a French colonial administrator stationed in the Comoro Islands. A local fisherman had captured another coelacanth. This time, the circumstances were different in every important way. The fish had reached shore with its body largely intact. Although still fresh, natural decay had already begun its relentless progress. Smith immediately understood the narrow window before him. At most, he believed only about 72 hours remained before the internal organs, lost forever in the first specimen, would again become scientifically useless. Reaching the remote islands presented another challenge altogether. Commercial travel could not deliver him there quickly enough. Every delay threatened to erase the very evidence he had spent 14 years pursuing. The urgency of the situation rose beyond ordinary academic concern and reached the highest levels of government. Through the personal intervention of the Prime Minister of South Africa, authorization was granted for a military aircraft to carry Smith across the Indian Ocean. What had begun as a handwritten sketch, preserved by determination, had grown into a journey spanning 14 years, carried by patience, conviction, and the belief that somewhere beneath distant volcanic seas, another impossible fish was still waiting. The journey unfolded with unusual speed for its time. Messages crossed governments instead of ordinary travel offices. Permissions were granted within hours instead of weeks. And a military transport aircraft lifted James Leonard Brearley Smith toward a chain of volcanic islands rising from the western Indian Ocean. Every stage of the flight carried the same urgency because the specimen waiting ahead was changing with every passing moment. The aircraft was a Dakota, operated by the South African Air Force, dispatched through extraordinary political cooperation. Commercial routes could not have delivered Smith in time, and the narrow opportunity to examine the fish before decomposition erased its remaining secrets, justified measures rarely taken for scientific work. By the time the aircraft descended toward the Comoro Islands, the success of 14 years of persistence rested upon what remained inside a single animal. When Smith finally stood before the specimen, years of determination gave way to emotion. Reports from those present recalled that he wept at the sight of it. Unlike the preserved fish waiting in the museum years earlier, this individual still carried the fragile biological evidence that had vanished from the first discovery. The long search had not merely produced another coelacanth, it had returned the missing half of a scientific story. The fish had been caught near Mutsamudu by a local fisherman named Ahmed Hussein Burrow. It measured approximately 1.42 meters in length, which is about 4.7 feet, and weighed roughly 43 kilograms, which is about 95 pounds. Though the tropical climate had already begun its steady work upon the body, enough of the internal anatomy remained preserved to permit the first comprehensive examination ever conducted on a living representative of this ancient lineage. As Smith and his colleagues began their study, familiar assumptions continued giving way to unexpected realities. The organs, skeletal organization, and internal structures differed markedly from those of modern fishes known through ordinary zoological study. This was not simply an unusual species hiding in deep water. It carried anatomical patterns inherited from an evolutionary branch that had persisted almost unchanged across immense stretches of geological time. Believing the specimen represented a distinct form, Smith initially assigned it the scientific name Melania anjuanae. Further research, supported by additional discoveries and careful comparisons, later demonstrated that both specimens belonged to the same living species, now recognized as Latimeria chalumnae. Science corrected itself as new evidence accumulated, refining classification without diminishing the extraordinary significance of the discovery itself. The second specimen also transformed understanding of the coelacanth's distribution. Between the year 1938 and the year 1975, 84 documented individuals would eventually be recorded, all originating from the Western Indian Ocean. What had first appeared to be an isolated biological miracle gradually revealed itself as a surviving population occupying a stable region rather than a single accidental refuge. Patterns emerged from each successive discovery. The volcanic slopes surrounding the Comoro Islands provided steep underwater terrain descending rapidly into deep water, with cave systems offering shelter beyond the reach of ordinary fishing activity. Generation after generation, the coelacanth had apparently continued its existence there, while the surface world remained entirely unaware. Perhaps the most revealing discovery came not from anatomy, but from conversation. Local fishermen already knew the animal well enough to give it a name. They called it gombessa and regarded it as an unremarkable catch. Its oily flesh possessed such an unpleasant taste that it held little value as food, and many considered it scarcely worth keeping. While museums across the world displayed fossil reconstructions beneath labels declaring the lineage extinct, coastal communities had occasionally encountered the living fish for generations without imagining that it represented one of the greatest zoological discoveries of the modern era. Knowledge had existed in two different worlds at once. One was written in scientific literature, the other carried through everyday experience beside volcanic shores, where an ancient survivor had never considered itself extraordinary at all. Seen beneath the water, the coelacanth carries the impression of an animal assembled according to an older design, one that followed a different architectural language before the familiar forms of modern fishes became widespread. Every surface and contour seems to preserve decisions made across a world far removed from the oceans of today. Yet each feature continues serving a living purpose rather than existing as a relic. Its body is broad, muscular, and surprisingly substantial, capable of reaching nearly 2 meters in length, which is about 6.6 feet, and weighing as much as 90 kilograms, which is about 198 pounds. Living individuals display a remarkable blue-purple coloration scattered with delicate white markings. Those pale spots differ from one animal to another, giving each fish an appearance as distinctive as weathered stone shaped by time. Against the dim waters of its deep volcanic home, the pattern breaks apart its outline, helping the animal merge with shifting light filtering down from far above. Covering the body are exceptionally thick scales, unlike those found on ordinary fishes. Their rigid structure resembles protective armor more commonly associated with long vanished vertebrates preserved in ancient rock formations. These are cosmoid scales, a form once widespread among prehistoric fishes hundreds of millions of years ago, but surviving today only in the coelacanth. Each overlapping plate contributes not only strength, but also a living connection to anatomical patterns that disappeared almost everywhere else long before humanity appeared. Behind the body extends one of its most distinctive features, a tail unlike that of any familiar modern fish. Rather than ending in the conventional two lobes seen across most marine species, the coelacanth possesses a trilobate tail with an additional central lobe projecting between the upper and lower sections. This unusual arrangement provides powerful yet remarkably stable propulsion, allowing the fish to move through deep water with measured control before accelerating in brief bursts whenever necessary. The remaining fins continue the impression that this creature belongs to a different chapter of vertebrate history. Two dorsal fins rise along the back, while paired pectoral and pelvic fins extend from the sides, accompanied by a single anal fin beneath the body. Instead of being supported mainly by slender rays, each paired fin grows from a fleshy, muscular lobe containing internal bones. Their movement reflects a structural complexity hidden beneath the skin, revealing an organization far removed from the simpler fin construction that dominates most living fishes. Running through the center of the body is another remarkable feature. The coelacanth lacks a true vertebral column supporting the body in the familiar manner found among most adult vertebrates. In its place lies a hollow tube filled with oil, known as the notochord. Rather than relying primarily upon rigid bone, the body gains support through internal pressure maintained within this flexible structure. It is an arrangement inherited from very early vertebrate ancestors, preserved across immense stretches of evolutionary history. The human body still carries a faint reminder of that ancient architecture. During early development, the notochord appears briefly before being replaced almost entirely by the vertebral column. Only a small remnant remains within the soft centers of the discs separating the spinal bones. In the coelacanth, that ancestral framework never disappears. It remains the principal support extending from head to tail throughout the animal's entire life. Even its colors tell a story that photographs rarely capture. The luminous blue-purple visible beneath the sea fades rapidly after death, gradually becoming shades of brown within only a few hours. By the time preserved specimens reached museums and scientific collections, much of their living appearance had already vanished. The remarkable fish resting before Marjorie Courtenay Latimer on that unforgettable day possessed colors that almost no preserved specimen would ever display again, leaving memory as the only place where its first living brilliance could endure. Movement often reveals relationships that outward appearance conceals. Bones may remain hidden beneath skin, and ancestry may disappear beneath millions of years of change. Yet the rhythm of motion can preserve an older memory with remarkable fidelity. In the coelacanth, one of the most profound connections in the history of life unfolds not through its shape alone, but through the measured sequence of its fins as it glides through deep water. The paired pectoral and pelvic fins do not move together in the manner expected of most fishes. Instead, they alternate diagonally. The front fin on one side advances with the rear fin on the opposite side, followed by the opposite front and rear pair. The pattern repeats with steady coordination, creating a balanced progression that differs strikingly from the synchronized fin strokes common among the vast majority of aquatic vertebrates. To an observer studying the sequence frame by frame, the motion appears unexpectedly familiar. It resembles the coordinated stride of a horse crossing open ground, the deliberate walk of a lizard over stone, or the natural rhythm carried within every human step. Although the environments could hardly be more different, the underlying coordination belongs to the same ancient pattern, preserved across hundreds of millions of years through entirely different ways of moving. That similarity reaches deeper than movement alone. Hidden within each fleshy lobe lies an internal arrangement of bones corresponding closely to the earliest structural blueprint of vertebrate limbs. A single upper bone extends outward before dividing into two lower elements, following the same fundamental organization that later appeared in the limbs of animals living upon land. In the forelimbs of terrestrial vertebrates, these bones became the humerus, followed by the radius and ulna. In the hind limbs, they developed into the femur, followed by the tibia and fibula. Within the coelacanth, those ancestral relationships remain visible in a form still serving life beneath the sea. Yet the fish itself never walks. It drifts through deep water, turning with measured precision among rocky slopes and volcanic caves. The lobed fins stabilize the body, guide slow changes of direction, and provide graceful control rather than supporting weight against solid ground. Their purpose belongs completely to an aquatic existence, even while their architecture preserves possibilities that would later unfold elsewhere. Far back during the Devonian period, approximately 375 million years ago, a close relative within the ancient lobe, finned lineage, began interacting with shallow substrates in a different way. Instead of relying entirely upon open water, those ancestral vertebrates gradually used similar paired appendages to push against mud, submerged vegetation, and the margins of ancient wetlands. Generation after generation, those movements became increasingly effective for supporting the body beyond buoyant water. From those experiments emerged the earliest terrestrial vertebrates, including primitive amphibians that carried the same alternating diagonal coordination onto land. Their steps marked one of the most significant transitions in the history of life, opening continents to entirely new forms of movement and eventually giving rise to reptiles, birds, mammals, and countless other descendants. Every person taking an ordinary step today participates in that ancient inheritance. The mechanics have changed through evolution, refined by muscles, joints, balance, and posture suited to upright walking. Yet, the underlying coordination still echoes a movement established long before forests covered the continents. It is not an imitation of the coelacanth's motion, but a continuation of the same deep evolutionary pattern expressed through a different body. Meanwhile, far below the surface, at depths approaching 200 meters, which is about 656 feet, the coelacanth continues its measured passage through volcanic chambers. Each alternating sweep of its paired fins preserves a living demonstration of a rhythm that has endured across geological ages, linking the drifting fish beneath the sea with every stride ever taken upon the land above. Among the many structures carried forward from an ancient world, none is more unexpected than a feature concealed entirely within the coelacanth's head. Nothing about its outward appearance immediately reveals this hidden mechanism. Beneath the heavy scales and powerful jaws rests an arrangement of bone, unlike that of any other living vertebrate, preserved across immense stretches of evolutionary time while disappearing from every other surviving branch of the vertebrate family. Running through the middle of the skull is a movable hinge known as the intracranial joint. Rather than forming one continuous rigid case surrounding the brain, the cranium is divided into two sections capable of flexing in relation to one another. This remarkable articulation remains unique among living vertebrates. No mammal, bird, reptile, amphibian, or other living fish possesses an equivalent structure functioning in the same way. Its purpose becomes clear during the instant of a feeding strike. As the lower jaw swings downward, the forward portion of the skull also rotates upward through the intracranial joint. Instead of opening only from below, the mouth expands from both directions at once. The entire front of the head briefly widens into an opening considerably larger than would otherwise be possible, allowing prey to be engulfed with extraordinary efficiency. The movement lasts only a fleeting moment, yet its precision reflects countless generations of refinement. Muscles, ligaments, and bones operate together with remarkable coordination, producing a rapid expansion that increases the effective gape without requiring an unusually elongated lower jaw. In the perpetual darkness of deep volcanic habitats, where opportunities to capture prey may be infrequent, such efficiency provides a meaningful advantage. Fossils reveal that this remarkable arrangement was once far less unusual. During the Devonian period, hundreds of millions of years ago, intracranial joints appeared across numerous ancient lobe-finned fishes and heavily armored vertebrate lineages. At that distant point in Earth's history, the hinged skull represented one successful solution among many different experiments in vertebrate design. Seas contained an astonishing diversity of anatomical forms, each exploring different ways of feeding, swimming, and surviving. As geological ages unfolded, however, those possibilities gradually narrowed. Lineages vanished, environments shifted, and surviving descendants followed different evolutionary paths. Throughout that immense transformation, vertebrate skulls increasingly became solid, unified structures. The movable hinge disappeared as separate bones fused together into the rigid architecture now shared by humans, reptiles, birds, amphibians, and virtually every other living vertebrate. The ancestral mechanism seemed to vanish completely from the living world. The coelacanth alone retained it. That simple fact carries unusual weight because it demonstrates that evolution does not always replace every successful design. Some structures disappear because circumstances change. Others remain because the environment continues rewarding them. Within the deep marine habitats occupied by the coelacanth, the hinged skull never became an obstacle demanding replacement. Instead, it continued performing its task with sufficient effectiveness that countless generations inherited the same remarkable arrangement. When the fish glides through darkness, approaching 200 meters, which is about 656 feet below the surface, little about its measured movements hints at the extraordinary mechanism concealed beneath its scales. Then, within an instant, the front of the skull rises, the lower jaw descends, and the ancient hinge performs exactly as it did for ancestors that lived long before forests spread across the continents. Every successful strike becomes more than the capture of a meal. It is the continued operation of an anatomical design that almost every other vertebrate lineage surrendered across the passage of deep time. Preserved within the coelacanth is not merely an unusual skull, but a functioning fragment of Earth's distant biological history, still opening and closing beneath the sea. With the same elegant purpose it possessed hundreds of millions of years ago. Long before bones came to dominate the bodies of vertebrates, support arrived in a simpler form. Deep within the coelacanth, concealed beneath layers of muscle and ancient scales, that earlier design still endures. It is not a relic preserved in stone or an echo visible only through fossils. It continues to bear the weight of a living animal, carrying forward an architectural solution that first appeared near the beginning of the vertebrate story. Most modern fishes regulate their position in the water with a gas-filled swim bladder. By increasing or reducing the amount of gas inside this organ, they adjust their buoyancy with remarkable precision, rising or descending through the water column while conserving energy. This elegant system has become one of the defining characteristics of countless modern fish lineages, supporting life across rivers, lakes, and oceans throughout the world. The coelacanth follows a different path. It does not rely upon a functional gas-filled swim bladder. Instead, much of its internal support and buoyancy comes from a large oil and fat-filled notochord extending through nearly the entire length of its body. Rather than serving merely as a temporary developmental feature, this structure remains active throughout adulthood, continuing the same essential role it fulfilled in distant ancestors hundreds of millions of years ago. The notochord predates the evolution of a true vertebral column. Among the earliest vertebrates, it formed the primary supporting axis of the body, flexible enough to bend during swimming while firm enough to maintain overall shape. Only later did vertebrae gradually evolve around this primitive rod, creating the stronger spinal columns familiar throughout most living vertebrate groups. In almost every surviving lineage, the older framework yielded to the newer one. Humans briefly carry this same ancient structure during the earliest stages of development. Within the embryo, the notochord appears before the backbone forms, helping organize the body plan as tissues and organs begin taking shape. As development continues, nearly all of it disappears, replaced by the vertebral column before birth. Only a small remnant remains in adulthood, preserved within the soft central region of each disc, separating neighboring vertebrae. Hidden within every human spine rests a faint reminder of that ancestral design. The coelacanth never completes that transition. Its notochord remains the principal internal support throughout its entire life, creating a remarkable bridge between the earliest vertebrates and the present day. Evolution did not erase this older solution because, within the stable conditions of its deep marine habitat, the ancient arrangement continued performing its role with remarkable effectiveness. Another feature preserved within the coelacanth carries an equally fascinating story. Buried beneath layers of fatty tissue lies the remnant of a lung. This organ no longer functions in breathing. It cannot extract oxygen from the air, nor does it expand and contract like the lungs of terrestrial vertebrates. Instead, it survives only as a vestigial structure, reduced almost beyond recognition, yet still present within the body. Its existence points toward ancestors that inhabited environments very different from the deep volcanic slopes occupied today. Shallow waters often experience changing oxygen levels as seasons shift, temperatures fluctuate, and plant life transforms surrounding conditions. In such habitats, an organ capable of assisting respiration could provide a valuable advantage. Across immense spans of evolutionary time, descendants gradually settled into deeper marine environments where that function became unnecessary. The organ diminished, yet it never vanished entirely. Within a single animal, the enduring notochord and the vestigial lung preserve two separate chapters of vertebrate history. One continues performing an ancient structural role, while the other remains as an enduring biological memory of environments left behind. Together, They reveal that the coelacanth is not simply a survivor from another age. Its body still carries the living record of evolutionary pathways that most other vertebrates have long since abandoned. Not every sense depends upon light. Far below the reach of daylight, where vision becomes increasingly limited, another stream of information flows continuously through the surrounding water. Every heartbeat, every muscle contraction, every impulse traveling along a nerve releases an electrical trace into the environment. The coelacanth inhabits this hidden landscape with an organ unlike that of any other living fish, perceiving signals that remain entirely beyond ordinary sight. Embedded within the front of its snout lies the rostral organ, a remarkable cavity filled with a specialized gelatinous material and connected to sensory cells capable of detecting weak electrical fields. Rather than functioning as an eye or an ear, this structure serves as an instrument for electroreception, allowing the fish to perceive the faint electrical activity naturally generated by nearby living animals. Every moving creature produces these subtle signals. As muscles contract and nerves transmit impulses throughout the body, minute electrical fields spread outward into the surrounding water. Although invisible, they create a constant pattern reflecting the presence of nearby life. The coelacanth does not rely upon reflected light to locate these hidden animals. Instead, it interprets the electrical signatures surrounding them, gathering information that remains inaccessible through ordinary vision alone. Within the darkness of its deep habitat, this ability becomes especially valuable. The fish often drifts slowly through the water, conserving energy while remaining alert to changes in its surroundings. Rather than searching across great distances, the rostral organ appears to function at close range, becoming most useful during the final moments before an attack. As prey draws near, the electrical pattern grows clearer, allowing remarkably accurate targeting even when visual detail is almost entirely absent. This specialized sense does not replace the coelacanth's other senses. Instead, it complements them, adding another layer of environmental awareness perfectly suited to life among deep volcanic slopes and rocky shelters. In places where shadows remain constant and visibility may shift with suspended particles or changing conditions, electrical perception provides dependable information that light alone cannot always supply. Electroreception has appeared elsewhere within the animal kingdom through different evolutionary pathways. Sharks employ sensitive organs distributed across their snouts to detect hidden prey beneath sand or within crevices. Electric eels perceive electrical changes while also generating powerful electrical discharges of their own. The platypus searches riverbeds using specialized receptors within its bill, while certain amphibians possess comparable sensory systems adapted to aquatic environments. The coelacanth, however, followed an entirely separate evolutionary course. Its rostral organ is not directly related to the electroreceptive structures found in sharks, amphibians, or any other living vertebrate. Although these systems accomplish similar tasks, they arose independently through separate histories, illustrating how evolution can repeatedly arrive at comparable solutions when different lineages encounter similar environmental challenges. The coelacanth did not inherit another animal's design. It developed its own distinctive answer to the demands of hunting where light offers little assistance. Observers have also documented another intriguing behavior. At times, the fish slowly assumes an almost vertical position, lowering its head toward the sea floor while remaining nearly motionless within the water. This unusual posture may allow the rostral organ to examine the sediments below more carefully, detecting the electrical traces of animals concealed beneath loose material or hidden among uneven volcanic rocks. Rather than sweeping rapidly through its surroundings, the coelacanth appears to investigate with remarkable patience, gathering delicate signals before making a measured approach. Across roughly 400 million years of evolutionary history, this remarkable sensory system has continued serving its ancient purpose. While continents shifted, climates transformed, and countless lineages appeared before disappearing again, the coelacanth retained a way of perceiving life that remains uniquely its own. Suspended within the darkness, it continues reading the living currents surrounding it, guided not by light alone, but by the faint electrical language carried endlessly through the sea. Long before researchers could recognize familiar faces beneath the sea, the coelacanth had already been carrying its own natural signature. Across the thick blue-purple scales scattered over its body, pale markings form an arrangement unlike that of any other individual. Each pattern is fixed, distinctive, and as reliable for identification as a fingerprint is among human beings. Two coelacanths may appear almost identical at first glance, yet careful comparison reveals that no pair shares precisely the same constellation of white spots. This discovery transformed the way scientists studied these elusive fish. Rather than attaching artificial tags or capturing animals repeatedly, researchers learned that a carefully taken photograph could preserve an individual's identity. Years later, another expedition returning to the same underwater caves could compare fresh images with earlier records and recognize the very same fish. The markings remained stable enough to follow particular individuals across long stretches of time without disturbing their natural behavior. With every successful identification, an invisible history slowly emerged. Individual coelacanths received names, accumulated observation records, and became familiar residents within their underwater neighborhoods. Scientists could document where a particular fish preferred to spend its daylight hours, which volcanic caves it occupied most frequently, and how often it appeared within certain stretches of coastline. Instead of studying an anonymous population alone, they began observing recognizable lives unfolding across many years. These long-term observations gradually revealed another remarkable characteristic. Coelacanths display strong site fidelity, returning repeatedly to the same volcanic cave systems that shelter them during daylight. Within these rocky chambers, they remain almost motionless, conserving energy before leaving after darkness settles above the sea. Their nightly movements extend outward into surrounding waters before eventually bringing them back to the familiar refuges they have occupied again and again. This dependable routine became visible only because each individual could be recognized without interference. One encounter alone offered only a fleeting glimpse. Repeated encounters with the same fish, separated by seasons and years, uncovered patterns impossible to detect through isolated observations. The ocean seemed less like an endless wilderness and more like a landscape of enduring homes occupied by long-lived residents following established paths. Growth studies added another dimension to this unfolding portrait. By examining growth rings preserved within the scales, researchers estimated that coelacanths may survive for 60 years or even longer. Such longevity places them among the more enduring fishes alive today, comparable with certain large sharks and sizable bony fishes. A creature first photographed during one generation of researchers may still be encountered decades later by another, continuing much the same rhythms beneath the sea. These discoveries also revealed how limited the surviving population truly appears to be. Around the Comoro Islands, only a relatively small number of coelacanths inhabit a restricted collection of volcanic cave systems. Individual recognition allowed researchers to avoid counting the same fish repeatedly while building increasingly accurate estimates of population size. Every familiar pattern of white markings became another carefully recorded presence within a community far smaller than anyone had once imagined. Among fishes, such individually distinctive markings are uncommon. Many species display characteristic stripes, bands, or spots shared broadly throughout the population, making one individual nearly impossible to distinguish from another without artificial tags. The coelacanth follows a different pattern. Its markings carry enough unique detail that each animal becomes visually recognizable through natural features alone, a characteristic whose biological significance scientists continue to investigate with growing interest. The result is a deeper appreciation of individuality within a lineage often described only through its immense age. Beyond its ancient anatomy and extraordinary history, every surviving coelacanth represents a single, identifiable life moving through familiar caves, returning to familiar waters, and leaving behind a visual record written across its own scales. The ancient lineage endures, yet it does so one distinct individual at a time. Far beyond the reach of ordinary observation, another chapter of the coelacanth's life unfolds, where no human eyes have yet witnessed it directly. The secluded volcanic caves that shelter these ancient fish during the daylight hours almost certainly guard their earliest beginnings as well. Within those hidden chambers, generation follows generation through a rhythm so gradual that even decades of scientific study have revealed only fragments of the full story. Unlike many familiar fishes that release eggs into open water, the coelacanth follows a far slower path. Fertilization takes place within the female's body, where each developing embryo remains enclosed inside its own egg rather than being deposited into the surrounding sea. The young continue growing there, nourished by the yolk stored within those eggs, until they emerge as fully formed offspring. This reproductive strategy, known as ovoviviparity, allows the developing young to complete their earliest stages within the protection of their mother, instead of facing the uncertainties of the open ocean immediately after fertilization. The pace of this process is extraordinary. Scientific evidence indicates that a female coelacanth carries her developing young for approximately 5 years before birth. Among fishes, this is one of the longest gestation periods ever documented. While countless generations of faster breeding species appear and disappear across the oceans, a single coelacanth mother may still be nurturing the same developing brood deep within her body, following a biological timetable measured not in seasons but in years. When birth finally approaches, the young are already remarkably developed. A female may carry anywhere between 5 and 26 offspring at one time. Each newborn measures approximately 30 centimeters, which is about 12 inches, to 38 centimeters, that is nearly 15 inches, in length. They enter the world not as fragile larvae drifting with ocean currents, but as miniature versions of their parents, already equipped with the distinctive lobed fins, thick scales, and ancient body design that have characterized their lineage across immense spans of geological history. Even so, the moment of birth itself remains unseen. No researcher has directly observed a female coelacanth giving birth in its natural habitat. Evidence strongly suggests that these events occur within the same deep volcanic cave systems that provide shelter during the day. These refuges typically lie between 150 meters, that is nearly 492 feet, and 300 meters, which is about 984 feet beneath the surface. Within those dim chambers, shielded from waves, sunlight, and nearly every human visitor, another generation quietly enters the sea, continuing a cycle that has likely persisted for hundreds of millions of years. Such patience carries a cost in the modern world. A reproductive strategy built upon lengthy investment leaves little opportunity for rapid recovery when individuals disappear. Every mature female represents years of biological commitment before even a single new generation can emerge. If adults are removed through accidental capture or other human pressures, replacements cannot appear within a single breeding season. The population must instead wait through another prolonged interval before those losses can begin to be repaired. This delicate balance explains why conservation scientists view every surviving coelacanth as profoundly important. The species inhabits only a limited number of suitable deep water environments, and each individual contributes meaningfully to the future of the population. A comparatively small decline may represent the disappearance of years of future reproductive potential, because every adult embodies an investment measured across many seasons before producing even a modest number of offspring. There is a gentle irony within this ancient rhythm. The same deliberate pace that may once have helped the coelacanth endure shifting continents, changing oceans, and repeated mass extinctions now leaves it less able to respond to the accelerated pressures of the present age. Its biological clock still moves with the cadence of deep time, preserving a life history shaped across countless ages, even as the world surrounding it changes far more rapidly than its patient inheritance ever anticipated. There are stories written in stone, preserved within ancient layers of rock, and there are stories written within living cells. For generations, the fossil record suggested that the coelacanth had changed with remarkable restraint across immense stretches of Earth's history. During the early years of the 21st century, researchers finally gained the opportunity to ask whether that extraordinary stability extended beyond its outward appearance and into the instructions carried within every cell of its body. In the year 2013, an international team of scientists published the complete genome sequence of the African coelacanth in the journal Nature. The achievement opened a new window into one of the oldest surviving vertebrate lineages. Instead of studying bones, scales, or preserved fossils, researchers could now examine the inherited biological code itself, comparing it with the genomes of many other living vertebrates to understand how the lineage had changed across hundreds of millions of years. The complete genome contained approximately 2.74 billion base pairs, placing it within a similar range to the human genome in overall size. That similarity did not imply close relationship, nor did it suggest that the two genomes carried identical information. Rather, it illustrated that complexity is not measured simply by size. The coelacanth possesses a genome every bit as intricate as those of other modern vertebrates, containing countless genes, regulatory regions, and repeating sequences working together to sustain a living animal. When scientists examined the protein coding genes in detail, an unexpected pattern emerged. The genes of the coelacanth had accumulated changes more gradually than those of any other vertebrate genome sequenced at that time. Evolution had certainly continued, because no living species remains completely unchanged. Yet the molecular pace of that change had been exceptionally restrained. The fossil record had already hinted at enduring anatomical stability. The genome now revealed that a similar pattern extended into the deepest biological instructions of the animal itself. This gradual molecular evolution does not mean that the coelacanth is primitive, incomplete, or somehow less advanced than other living creatures. Every organism alive today has experienced the same uninterrupted span of evolutionary history since its ancestors diverged from those of every other species. The distinction lies not in age or sophistication, but in the intensity of evolutionary pressures. Within the deep volcanic environments occupied by coelacanths, many of the forces that drive rapid adaptation elsewhere appear to have remained comparatively consistent across immense intervals of time. The genome also revealed remarkably low genetic diversity among the individuals examined. Such limited variation suggests that surviving populations have remained relatively small, or that the lineage has experienced an unusually slow accumulation of genetic differences over millions of years. A restricted gene pool does not erase the resilience demonstrated throughout geological history. Yet, it does indicate that the modern population possesses less flexibility when responding to sudden environmental disturbances than a more genetically diverse species might enjoy. Another notable feature emerged from the analysis. Approximately 60% of the genome consists of repetitive genetic elements, sequences copied many times throughout the hereditary material. Genomes containing substantial proportions of these repeating regions are often associated with lineages that have remained comparatively stable over prolonged evolutionary timescales. These repeated sequences do not represent useless clutter. Many continue to influence how genes are organized, regulated, and expressed, contributing to the overall architecture of the genome. Taken together, these discoveries offered molecular confirmation of what ancient fossils had been suggesting for generations. The coelacanth has never been suspended outside evolution. Instead, it has occupied an environment where successful biological solutions have required comparatively little revision across extraordinary spans of time. Its genome continues to change, yet with uncommon patience, reflecting a lineage that has not escaped time, but has experienced its passing according to a rhythm unlike almost anything else among living vertebrates. Within every living cell of the coelacanth lies a collection of inherited instructions that extends far beyond the needs of its present existence. The genome does not simply describe the animal as it is today. It also preserves traces of journeys taken by distant ancestors, carrying fragments of biological history across spans of time so immense that the environments which first shaped those instructions have long since disappeared. As researchers continued examining the complete genome in greater detail, they encountered an unexpected collection of genes associated with the sense of smell. The coelacanth possessed numerous olfactory receptor genes, including receptors closely resembling those found in four-limbed vertebrates that detect odor-carrying molecules moving through air rather than dissolved through water. Discovering such receptors within a modern marine fish immediately attracted scientific attention because they appeared strangely out of place within an animal that spends its entire life in the deep ocean. The finding does not mean that the living coelacanth rises from volcanic caves to breathe the atmosphere or sample scents drifting above the waves. These receptors do not transform the fish into an air-breathing hunter. Instead, they provide evidence preserved within the genome itself, suggesting that somewhere along the evolutionary history of the lobe-finned lineage, ancestors occupied environments where sensing compounds carried at the boundary between air and water offered a genuine biological advantage. Such habitats likely included shallow coastal waters, estuaries, tidal margins, or other places where changing water levels repeatedly exposed organisms to conditions unlike those found in the permanent darkness of the deep sea. Within those ancient environments, natural selection favored sensory systems capable of interpreting chemical information that later generations would no longer require after returning to deeper marine habitats. Yet the underlying genetic architecture did not disappear entirely. It remained embedded within the hereditary record, surviving long after its original purpose had faded from everyday life. This persistence reflects an important principle of evolution. Not every inherited feature vanishes immediately when its usefulness declines. Genes may remain for immense periods if they create no significant disadvantage, becoming enduring echoes of earlier chapters in a lineage's history. The coelacanth has inhabited deep salt water for tens of millions of years, yet portions of its genome still preserve molecular reminders of ancestors that encountered a very different world near the surface. The genome revealed another discovery equally compelling. Scientists identified regulatory elements associated with limb formation that are conserved between the coelacanth and land-dwelling vertebrates. These regulatory sequences act as genetic switches, controlling when and where particular developmental genes become active during embryonic growth. Comparable regulatory elements are absent from the ray-finned fishes that dominate modern oceans, lakes, and rivers, highlighting a profound distinction between these great branches of vertebrate evolution. The coelacanth does not grow legs. Its embryos develop the familiar lobed fins that have characterized the lineage throughout recorded history. Yet the genetic mechanisms involved in organizing those fins retain deep similarities to the developmental systems later used in vertebrates that eventually walked across land. The connection exists not because the coelacanth stands midway between fish and terrestrial animals today, but because both inherited important developmental instructions from shared evolutionary ancestors living hundreds of millions of years ago. Seen together, these discoveries transform the genome into something resembling an ancient archive rather than a simple instruction manual. Every generation faithfully copies sequences that continue serving present biological functions, while also preserving inherited frameworks shaped by vanished environments. The coelacanth carries no conscious memory of shallow shorelines or ancestral transitions toward the margins of land. Nevertheless, its hereditary code continues to bear enduring witness to those distant chapters, preserving genetic patterns that bridge the deep ocean of today with evolutionary landscapes that existed long before the modern world had taken shape. For decades, one of the deepest questions in vertebrate biology rested not beneath the sea, but within museum collections, research laboratories, and the pages of evolutionary studies. Scientists agreed that the ancestors of all land-dwelling vertebrates had emerged from the ancient lobe-finned fishes, yet uncertainty remained over which living survivor stood nearest to that remarkable turning point. The coelacanth seemed an obvious candidate because its body retained so many ancient features, but another contender, the lungfish, carried its own compelling evidence. The distinction mattered because the answer would shape how researchers reconstructed one of the greatest transformations in the history of life. Understanding which modern lineage shared the closest relationship with the first vertebrates to conquer land would provide a clearer window into the biological innovations that made forests, grasslands, and eventually humanity itself possible. For many years, anatomical studies pointed in different directions. Certain skeletal characteristics appeared to favor the coelacanth, while other structures suggested the lungfish occupied the nearer branch. These competing interpretations persisted because physical appearance alone cannot always reveal the complete story of ancestry. Evolution sometimes preserves ancient forms with remarkable fidelity, while altering underlying relationships in ways that bones alone cannot fully resolve. Organisms that seem outwardly similar may have separated much earlier than expected, while others that appear more specialized may actually share a more recent common ancestor. The question waited patiently for evidence capable of reaching beyond anatomy into the inherited record carried inside every living cell. That evidence arrived through comprehensive genome sequencing. In the landmark study published during the year 2013, researchers compared the complete genetic information of the African coelacanth with that of many other vertebrates. Their analysis examined 251 carefully selected genes across 22 vertebrate species, creating one of the most detailed evolutionary comparisons ever assembled for this question. The resulting genetic tree produced a clear conclusion that ended a debate stretching across generations of scientific investigation. The lungfish, not the coelacanth, proved to be the closest living relative of four-limbed vertebrates. Its lineage branches nearer to the common ancestor that eventually gave rise to amphibians, reptiles, birds, and mammals. The coelacanth occupies the neighboring branch, representing the closest surviving relative of the shared ancestral population that existed immediately before the evolutionary paths of lungfish and future land vertebrates separated from one another. Rather than diminishing the importance of the coelacanth, this discovery refined it. The animal is no longer viewed as a living stand-in for the first creature that climbed onto land. Instead, it offers an extraordinary glimpse into the biological condition that existed just before that decisive divergence. It preserves many characteristics inherited from a population standing near one of evolution's greatest crossroads, allowing researchers to examine features present before one branch continued toward terrestrial life, while another remained devoted to the sea. The genome also illuminated another important chapter within the story of limb evolution. Researchers identified conserved regulatory elements associated with the development of limbs, including enhancer regions linked to the genes known as bone morphogenetic protein, 7, and Gly family zinc, finger 3. These genetic switches are shared by the coelacanth and land vertebrates, but are absent from the ray-finned fishes that dominate modern aquatic ecosystems. Their presence demonstrates that essential components of the developmental framework required for complex limbs were already established before vertebrates first stepped onto land. Within the sheltered darkness of volcanic caves, the coelacanth continues its measured existence, unaware of the remarkable inheritance carried within every cell. Hidden inside its genome are enduring developmental instructions preserved across hundreds of millions of years, not as promises of future change, but as enduring records of an ancestral design from which countless hands, wings, paws, and feet would eventually emerge. The story widened not through an expedition planned over many years, but through an unexpected moment during the beginning of a marriage. In the month of September, during the year 2997, marine biologist Mark Erdman and his wife Arnaz were spending their honeymoon in Sulawesi, surrounded by volcanic shores and warm tropical waters. Scientific discovery was not on the itinerary, yet the sea has often revealed its greatest secrets when no one expected to receive them. While walking through a fish market in the city of Manado, Arnaz noticed an unusually large fish being pushed past on a cart. Its heavy body and fleshy fins immediately seemed unlike the familiar catch displayed around it. She drew her husband's attention before the animal disappeared into the busy market. Erdman managed to photograph it only moments before it was sold. The shape echoed the unforgettable outline of the African coelacanth, yet one striking difference stood out. This fish carried a rich brown coloration rather than the deep blue shades associated with its African relative. The brief encounter lingered in his thoughts long after the market had returned to its ordinary rhythm. A single photograph could not confirm such an extraordinary possibility, and memory alone was not enough. Rather than making bold claims, Erdmann began speaking with local fishermen, learning about their catches, and listening carefully to stories passed between generations. Piece by piece, fragments of local knowledge suggested that the strange fish might not have been an isolated accident, but part of a hidden population inhabiting nearby volcanic waters. Many months later, during the month of July, in the year 2998, fortune returned. A fisherman named Omlame Sonatham caught another unusual fish near the volcanic island of Manado Tua. This time, word reached Erdmann before the animal was lost. He hurried to the location and found the remarkable survivor still alive. Placed within a tidal pool, it remained alive for approximately 6 hours, providing an opportunity that earlier generations of researchers could scarcely have imagined. During those precious hours, extensive photographs captured details impossible to preserve in preserved museum specimens alone. Researchers observed the graceful movement of its paired fins as it drifted through the water with deliberate control. The animal displayed the same distinctive style of locomotion that had fascinated scientists studying its African relative, offering another living glimpse into an ancient branch of vertebrate history before the opportunity faded with the passing of time. Careful examination followed, combining visible anatomy with detailed genetic analysis. The evidence pointed toward an extraordinary conclusion. This was not merely another population of the African species known as Latimeria chelumnae. Instead, it represented a distinct species, formerly named Latimeria menadoensis, the Indonesian coelacanth. Its brown coloration consistently distinguished it from the blue African form, while subtle anatomical and genetic differences confirmed that the two lineages had followed separate evolutionary paths for immense spans of geological history. Its known distribution extends along the volcanic coasts of North Sulawesi, Papua, and neighboring islands. Once again, the pattern appeared remarkably familiar. Like the African species inhabiting the volcanic landscapes of the Comoro Islands, the Indonesian coelacanth seemed closely associated with underwater volcanic formations, where deep caves and steep rocky slopes provide stable shelter beyond the reach of most surface disturbances. The comparison between the two species revealed another remarkable layer of their history. Although separated by roughly 10,000 kilometers, which is about 6,214 miles, of open ocean, their genomes remain approximately 98.7% identical. Such similarity reflects the unusually slow pace of genetic change already revealed through earlier studies. They diverged into separate species, yet each lineage carried forward much of the same ancient biological inheritance. Across vast distances and countless generations, both continued their patient existence beneath volcanic seas, preserving parallel chapters of a story that had begun hundreds of millions of years before any human eye first recognized either of them. The map had become far larger than anyone first imagined. What once appeared to be a single improbable refuge slowly expanded into a broad sweep of ocean stretching across thousands of kilometers, revealing that the coelacanth had never entrusted its future to one isolated sanctuary alone. Instead, it endured within scattered volcanic landscapes separated by immense reaches of open water, each population hidden behind the same patient rhythm of depth, darkness, and stone. The distance between the Comoro Islands, where the African coelacanth is most strongly associated, and the waters surrounding North Sulawesi, home of the Indonesian species, measures roughly 10,000 kilometers, which is about 6,214 miles. Between these distant regions lies nearly the full breadth of the Indian Ocean, an enormous expanse crossed by shifting currents, changing climates, and countless generations of marine life. Yet across that remarkable separation, members of the same ancient lineage continued to survive, each following a path established long before human history began. As additional discoveries accumulated after the original specimen was recognized, the known range of the African species steadily widened. Confirmed records extended beyond the Comoro Islands to the coasts of Kenya, Tanzania, Mozambique, Madagascar, and South Africa. Each new finding added another point to a growing constellation, demonstrating that the surviving population occupied a much broader region than anyone had believed during the earliest years of research. The picture no longer resembled a single hidden pocket of survival. It resembled a fragmented network of enduring habitats connected by deep geological time rather than by human observation. The discovery of the Indonesian species transformed that understanding even further. It showed that coelacanths had not persisted within one forgotten corner of the sea while vanishing everywhere else. Separate populations had continued across multiple ocean systems, maintaining their existence in environments spread across extraordinary distances. Their persistence suggested that the conditions supporting their survival were not unique to one location, but instead appeared wherever deep volcanic coastlines provided the shelter and stability their ancient biology required. What makes this realization especially remarkable is that these waters were never beyond the reach of people. The Western Indian Ocean, the Mozambique Channel, and the seas surrounding Indonesia have supported fishing communities, commercial shipping, scientific expeditions, and maritime travel for generations. Countless vessels crossed these waters, while nets descended repeatedly into productive fishing grounds. Even so, the coelacanth remained almost entirely beyond notice, not because humanity ignored these oceans, but because the animal occupied a world that ordinary exploration rarely entered. During daylight hours, coelacanths spend much of their time resting within deep volcanic caves and rocky overhangs, emerging mainly after darkness settles over the surface. Their preferred depths commonly place them far below the limits of conventional diving, where sunlight fades into a dim blue twilight before disappearing altogether. Combined with their slow movements and scattered populations, these habits made them functionally invisible despite living beneath seas that humans believed they understood. The hidden scale of that survival became even clearer during the year 2025. Divers participating in the Unseen Expeditions project succeeded in recording the first footage of a living Indonesian coelacanth within its natural habitat in the North Maluku archipelago. Rather than observing an individual brought accidentally to the surface, researchers watched the fish moving through the environment where it had always belonged. Those images extended the known distribution of the Indonesian species and revealed another fragment of a story that had remained concealed beneath volcanic seas for millions upon millions of years. Across two ocean basins, separated by vast distances yet united by the same ancient design, the coelacanth endured without announcing its presence. Its greatest disguise was never extraordinary speed, overwhelming numbers, or inaccessible wilderness. It was the simple persistence of a life lived beyond ordinary reach, within landscapes that allowed an ancient lineage to remain present while passing almost unnoticed through the unfolding ages of the modern world. Some discoveries remain forever tied to distance. The closer the coelacanth comes to human hands, the farther it moves from the conditions that have sustained it for hundreds of millions of years. For nearly every other living fish, capture offers an opportunity for prolonged study. For the coelacanth, Capture marks the beginning of an irreversible decline. Every attempt to maintain a living coelacanth in captivity has ended in failure. Individuals brought toward the surface have survived only for brief periods, with the longest documented cases lasting no more than a few hours. Even under the most careful handling, the transition out of the deep sea begins a chain of physiological changes that cannot be stopped. The animal arrives alive, yet the environment that shaped every aspect of its body has already been left behind. The principal challenge is pressure. Coelacanths normally inhabit waters between 100 and 400 meters in depth. At those levels, the surrounding water exerts approximately 10 to 40 times the pressure experienced at the surface. Every tissue, every internal cavity, and every chemical balance within the body has adapted to those immense forces. Pressure is not simply an external condition. It is woven into the ordinary function of the animal itself, as fundamental as the water surrounding it. As the ascent begins, that balance starts to unravel. Scientists believe the rapid reduction in pressure disrupts blood chemistry, interferes with buoyancy regulation, and impairs the nervous system. Organs that function normally in the deep sea are suddenly operating under conditions they never evolved to withstand. Unlike many shallower marine species that tolerate movement through changing depths, the coelacanth appears to possess remarkably little capacity to compensate for such an extreme environmental shift. Once these internal processes begin to fail, returning the animal to deeper water has not been shown to restore normal function. This limitation has shaped nearly everything known about the species. Every living coelacanth carefully examined by researchers has been observed either within its natural habitat through underwater technology or during the brief interval after accidental capture, before its condition rapidly deteriorated. No scientist has watched a healthy coelacanth continue its ordinary life inside an aquarium for days, weeks, or months. The familiar methods used to study many rare animals simply do not exist for this ancient fish. For much of the modern scientific era, even seeing a living coelacanth behaving naturally remained beyond reach. Meaningful observations within its own environment did not become possible until the closing decades of the 20th century, when deep diving submersibles and remotely operated underwater vehicles gradually extended human vision into habitats previously inaccessible. Those pioneering expeditions provided the first sustained glimpses of animals resting among volcanic caves, drifting with measured movements through the surrounding water, and leaving their shelters after darkness settled over the sea above. Even then, the observations remained limited. Cameras could remain only for restricted periods, and expeditions demanded considerable planning, specialized equipment, and favorable conditions. Much of the coelacanth's daily existence still unfolded beyond human sight. Behaviors, such as its distinctive head-down posture, its deliberate nighttime hunting, and its repeated use of particular cave systems, emerged slowly from many separate encounters, each contributing another small fragment to a picture that continues to develop with remarkable patience. There is a gentle irony within this enduring relationship between observer and observed, a lineage capable of surviving continental rearrangements, mass extinctions, and immense stretches of geological time proves unable to endure a single afternoon beneath the conditions that humans consider ordinary. The surface world that supports countless forms of life is, for the coelacanth, an environment as foreign as any distant planet. Its greatest protection has never been strength or speed, but complete fidelity to a realm whose pressures still refuse to loosen their ancient hold. There are moments in natural history when survival itself begins to look almost impossible. A lineage crosses unimaginable spans of time, endures continents breaking apart, witnesses oceans opening and closing, and continues almost unchanged into the present. Then, within the briefest instant of geological time, its future becomes uncertain through forces that never existed before. Both living species of coelacanth are now classified as critically endangered by the International Union for Conservation of Nature. For the African coelacanth, the situation is especially delicate. Current scientific estimates suggest that only about 300 individuals remain. Such a population is not simply uncommon. It exists at a level where the accidental loss of only a handful of adults during a single year represents a measurable fraction of the entire species. Unlike many fishes pursued by commercial fleets, the coelacanth has almost no value as food. Its flesh contains large quantities of oils and waxy compounds that produce an unpleasant taste and have been reported to cause severe gastrointestinal illness when eaten. Fishing communities have therefore never sought it deliberately as a valuable catch, yet this apparent lack of interest has not guaranteed safety. Instead, the greatest danger arrives by accident. Deep-line fishermen searching for valuable species, such as oilfish, lower their equipment into the same depths where coelacanths spend their lives. Hooks intended for entirely different animals occasionally find an ancient survivor drifting through the darkness. By the time the unexpected catch reaches the surface, the outcome is almost always irreversible. The fish cannot tolerate the dramatic change in pressure, and even immediate attempts to return it to deeper water have not restored normal function. As fishing technology has gradually extended into greater depths throughout the western Indian Ocean, places that once lay beyond regular human reach have become increasingly accessible. Small-scale fisheries and larger commercial operations now work in waters that overlap with habitats previously protected by nothing more than their remoteness. The volcanic slopes and submerged cave systems that sheltered coelacanths for immense stretches of time no longer exist beyond the influence of modern equipment. This creates a challenge unlike that faced by faster reproducing marine animals. A coelacanth invests approximately 5 years in producing a relatively small number of offspring. Every mature adult therefore represents decades of growth and an extraordinary commitment of biological resources. When one breeding individual disappears, the loss cannot be replaced within a single season or even within several years. Recovery unfolds at a pace measured across generations, while accidental mortality can occur within a single fishing trip. International agreements recognize this vulnerability. The African coelacanth is included within the first appendix of the Convention on International Trade in Endangered Species of Wild Fauna and Flora, placing the highest level of restriction on commercial international trade. These protections acknowledge the importance of preserving one of Earth's most distinctive evolutionary lineages. Yet regulations alone cannot eliminate every unintended encounter, particularly across extensive deep water regions surrounding the Comoro Islands and portions of the Tanzanian coastline, where monitoring remains difficult and fishing activity continues over wide areas. The contrast is almost impossible to ignore. This lineage endured the 5 great mass extinctions that reshaped life across the planet, including the asteroid impact that ended the age of the non-avian dinosaurs. It persisted through environmental upheavals beyond ordinary imagination because its hidden world remained remarkably stable. Today, the greatest uncertainty comes not from volcanic eruptions, shifting continents, or celestial collisions, but from expanding human activity reaching ever farther into the deep ocean. The same waters that protected the coelacanth for hundreds of millions of years have become increasingly connected to the surface above, where every advance in technology narrows the distance between one of Earth's oldest survivors and the modern world. Sometimes, the greatest influence of a living creature is not found within its own body, but within the questions it compels science to ask. The coelacanth transformed more than textbooks about ancient fishes. It reshaped the way researchers interpret absence itself, revealing that what cannot be found is not always truly gone. From this realization emerged the scientific concept known as the Lazarus taxon. The expression describes a species, or even an entire evolutionary lineage, that disappears from the fossil record for an immense span of time before eventually being discovered alive. Variations of this idea had circulated among paleontologists before the coelacanth entered the modern scientific world, but no example carried the same persuasive force. The rediscovery of an animal believed lost since the age of the non-avian dinosaurs gave the concept its defining symbol and permanently established its place within scientific thought. Before the discovery, during the 20th century, the reasoning surrounding extinction appeared relatively direct. Fossils documented the presence of a species through successive layers of rock. When those remains ceased after a particular geological interval, the simplest conclusion followed naturally. The lineage had vanished at roughly that point in Earth's history. The fossil record was treated as a reasonably continuous narrative, interrupted only by the inevitable gaps produced through erosion or incomplete preservation. The coelacanth introduced an essential note of caution into that interpretation. Its fossil record appeared to end roughly 65 million years ago, yet living populations continued inhabiting the deep ocean beyond every human expectation. Their existence demonstrated that disappearance from the geological record does not always coincide with biological extinction. Another possibility must always be considered. A lineage may continue surviving in places where the processes responsible for fossil formation seldom operate. Deep marine environments provide exactly such conditions. Far below the productive continental shelves, the accumulation of sediments capable of preserving large vertebrates is often limited or disturbed. Organic remains are consumed, scattered, or broken down long before they become enclosed within stable geological layers. Even when burial eventually occurs, the resulting deposits may remain inaccessible beneath immense depths of water for millions of years. Entire populations can therefore live, die, and vanish without leaving fossils that later generations are likely to discover. The coelacanth occupied precisely this hidden setting. Sheltering among volcanic cave systems beneath the deeper layers of the ocean, it lived within habitats where opportunities for long-term preservation were remarkably scarce. Its apparent absence from younger rocks did not reflect an absence from Earth itself. The record had not been deliberately erased. It had simply been written in places that science had not yet learned to read. This insight continues to influence paleontology far beyond the story of a single fish. Every interval where fossils suddenly disappear now carries an additional possibility alongside extinction. Researchers must consider whether environmental change altered preservation conditions, whether surviving populations retreated into poorly sampled habitats, or whether future discoveries may eventually reconnect an apparently broken evolutionary history. The fossil record remains an extraordinary archive, but it is no longer interpreted as an infallible census of every lineage that has ever lived. None of this diminishes the overwhelming reality that countless species truly have vanished forever. Most disappearances recorded in stone still represent genuine extinction. Yet, the coelacanth introduced a lasting measure of scientific humility. Absence can signify death, but it can also reflect geography, preservation, or the immense limits of human exploration. Somewhere between those possibilities lies a reminder carried from the deep ocean into every museum collection and every excavation site that the history of life is preserved not only by what the rocks contain, but also by the extraordinary places where rocks reveal almost nothing at all. A fossil can seem wonderfully permanent, preserved in stone long after the living creature has vanished. Yet every fossil also represents an extraordinary accident, the successful conclusion of a chain of events so improbable that its greatest lesson may lie not in what survives, but in everything that disappears without leaving the slightest mark. The rediscovery of the coelacanth encouraged paleontologists to examine this process with renewed care. Rather than treating the fossil record as a complete archive interrupted only by occasional missing pages, scientists increasingly recognized it as a remarkable collection assembled through countless unlikely circumstances. Each preserved skeleton reflects not only the existence of an organism, but also an exceptional sequence of environmental conditions extending across immense spans of geological time. For fossilization to occur, a dead animal must avoid rapid destruction. Its remains usually require swift burial beneath sediment before scavengers, currents, and microbial activity remove the evidence. The surrounding chemistry must favor preservation rather than decay. Pressure and temperature over millions of years must remain suitable for mineral replacement instead of complete destruction. Finally, those ancient rocks must survive mountain building, erosion, and countless geological changes before eventually becoming exposed where human observers can discover them. Failure at any point along this immense sequence leaves no fossil behind. Because these requirements are so demanding, scientists understand that the fossil record preserves only a minute fraction of the species that have ever lived. Most organisms complete their entire existence without contributing even a single trace to Earth's geological archive. They die, decompose, and return their materials to the living world, leaving history to continue without physical evidence of their presence. Deep marine habitats make preservation even less likely. Many regions beneath the thermocline possess conditions that rarely favor long-term fossil formation. Organic remains may be consumed before burial occurs, while slow sediment accumulation limits opportunities for rapid preservation. Even when material eventually settles upon the sea floor, later geological processes may never bring those deposits within reach of scientific investigation. Vast stretches of deep ocean, therefore, remain represented by remarkably few fossils compared with shallower environments. The coelacanth spent tens of millions of years inhabiting precisely such settings. Sheltering within volcanic cave systems below the layers most frequently sampled by both nature and science, it occupied one of the least favorable environments imaginable for producing an accessible fossil record. Its apparent disappearance after the closing chapters of the Age of the Dinosaurs reflected not an evolutionary ending, but an extraordinary absence of preservable evidence. Following the rediscovery of the coelacanth, researchers also identified additional examples of organisms whose fossil histories contained unexpectedly long interruptions. Some lineages, once believed extinct, were eventually discovered alive. Others gained newly recognized fossil evidence that filled previously mysterious intervals. These examples differed greatly in age, habitat, and evolutionary history, yet together they reinforced a shared lesson. Geological absence alone cannot always distinguish between extinction and incomplete preservation. The coelacanth remains the most celebrated illustration of this broader principle because its story unfolded with exceptional clarity. Its survival transformed an abstract limitation into an unforgettable reality. Instead of exposing a weakness within science, the discovery strengthened scientific understanding by revealing where interpretation required greater care and where certainty had previously extended beyond the available evidence. Today, whenever paleontologists conclude that a lineage disappeared after its final known fossils, that conclusion is presented with greater precision than before. Fossil absence remains one of the strongest forms of evidence available for reconstructing Earth's past. Yet, it is understood within the boundaries of what the rocks can truly reveal. Beyond those boundaries stretches an older and far larger world where countless lives unfolded without preservation, reminding us that deep time has always contained more history than stone alone can record. Far beneath the familiar movements of waves and weather lies a realm whose greatest defining feature is not its darkness, but its constancy. While continents drift, climates fluctuate, and entire ecosystems rise and vanish, these deeper waters change at a pace that seems almost detached from the restless rhythm above. The persistence of the coelacanth invites a broader reflection, not only about one remarkable animal, but about the nature of the deep ocean itself. Across depths between 200 kilometers, which is about 124 miles, and 400 kilometers, that is nearly 249 miles, conditions remain consistently cold, heavily pressurized, and almost untouched by the daily cycles that shape surface life. Within volcanic cave systems, sheltered beneath the thermocline, the surrounding environment has retained a remarkable stability across immense spans of geological history. Evolution still proceeds there, yet many of the forces demanding rapid adaptation become less intense than they are in shallower seas, where changing temperatures, shifting coastlines, and seasonal variation constantly reshape the rules of survival. This difference became especially meaningful at the close of the age of the dinosaurs, when the asteroid responsible for the Cretaceous-Paleogene extinction struck Earth. The consequences transformed the surface of the planet. Vast quantities of debris entered the atmosphere, reducing sunlight across much of the globe. Wildfires spread across enormous regions of land. Food webs built upon photosynthesis weakened as sunlight struggled to reach plants and microscopic algae. Countless terrestrial and shallow marine species found themselves facing conditions unlike any they had previously endured. The deepest marine habitats experienced those events through a different pathway. They still depended upon the broader ocean for nutrients, and no environment remained completely untouched by a planetary catastrophe. Yet, beneath the thermocline, immediate disruption became greatly softened. The crushing weight of the water formed a natural barrier separating those communities from the direct violence unfolding far above. Within volcanic landscapes, additional sources of chemical energy continued supporting local ecosystems through chemosynthetic organisms that relied upon dissolved minerals rather than sunlight as the foundation of their existence. The coelacanth, therefore, did not survive by overcoming the extinction through extraordinary strength or exceptional resilience alone. It survived because its chosen world occupied a portion of the planet where the most destructive effects arrived diminished. Its refuge was not perfect protection, but enough stability remained for ancient biological rhythms to continue, while life nearer the surface entered one of the greatest crises in Earth's history. Viewed through this perspective, the deep ocean becomes something very different from the empty wilderness it was once imagined to be. It emerges instead as a vast biological reservoir, preserving lineages across intervals of time that erased countless relatives elsewhere. Stability itself becomes an ecological resource, allowing successful body plans to remain effective across millions of years without demanding dramatic transformation. The coelacanth is not entirely alone in illustrating this pattern. Certain ancient sharks, enduring groups of marine invertebrates, and numerous microscopic organisms also display histories, suggesting that deeper habitats have repeatedly served as sanctuaries during periods of widespread environmental upheaval. Their evolutionary stories differ greatly, yet they converge upon the same underlying principle. The farther one descends into these enduring waters, the more the pace of environmental change begins to soften. The fish resting among volcanic stone therefore represents more than a remarkable survivor. It reflects the character of the place that sheltered it. The deep ocean preserves possibilities that the surface cannot always sustain, carrying living chapters from distant ages into the present day. Within those enduring depths, time does not stop, yet it unfolds with remarkable patience, allowing ancient forms to remain part of a living world while the face of Earth above continues its endless transformation. Long after the coelacanth ceased to be regarded as an impossible survivor, another realization settled into marine science with equal force. The greater discovery was not merely that one ancient fish had endured, but that the ocean had preserved its existence without revealing it to humanity for millions upon millions of years. That realization continues to shape every descent into the deeper reaches of the sea. The ocean covers roughly 71% of Earth's surface, yet its greatest dimension is not its breadth, but its depth. Beneath approximately 200 meters, which is about 656 feet, the overwhelming majority of the planet's habitable volume begins. Nearly all of the living space available for complex marine life exists below that boundary, extending downward through immense regions that remain only sparsely explored. Vast stretches have never been observed directly by human eyes, and many have been visited only once, if at all. Within that immense volume, scientists estimate that only a modest fraction of deep-sea species has been formally described. Every research expedition descending into abyssal plains, volcanic trenches, cold seeps, hydrothermal environments, and isolated submarine mountains continues to recover organisms unknown to science. Some differ only subtly from familiar relatives. Others appear so unusual that they reshape existing branches of the evolutionary tree. The catalogue of life remains unfinished because the landscape containing much of that life remains largely beyond regular observation. The circumstances that concealed the coelacanth were never uniquely its own. Great depth, perpetual darkness, rugged volcanic terrain, and a complete absence of dependence upon surface waters formed an effective shield against casual discovery. Those same conditions extend across countless regions of the global ocean. Many habitats remain difficult to sample with nets, difficult to image with cameras, and difficult even to locate with confidence beneath the shifting contours of the seafloor. The lesson reaches beyond fishes alone. Species belonging to entirely different branches of life have also vanished from the fossil record before later being encountered alive. Certain plants, marine invertebrates, and microscopic organisms have each demonstrated that apparent disappearance does not always signify true extinction. Sometimes it reflects the simple reality that an organism occupies environments where preservation into fossils is extraordinarily uncommon, or where living populations remain isolated from routine scientific observation. For that reason, the rediscovery of the coelacanth accomplished something greater than restoring a single lineage to biology. It demonstrated that the inventory of life cannot be completed merely by studying museum collections or reviewing known fossils. Discovery also depends upon reaching places where observation has scarcely begun. Each unexplored habitat represents not an empty space upon a map, but a chapter whose contents remain unread. Modern expeditions continue to reinforce that understanding. Vehicles carrying cameras descend through immense water columns and return with images of unfamiliar animals drifting above the seabed. Samples collected from brine pools reveal communities unlike those inhabiting surrounding waters. Remote volcanic landscapes shelter species found nowhere else. Even now, scientific papers describing newly recognized deep-sea organisms appear with remarkable regularity, each one adding another thread to an unfinished tapestry woven across the largest environment on Earth. The coelacanth therefore stands not as an extraordinary exception interrupting an otherwise complete understanding of nature. It serves instead as evidence that incompleteness is itself an enduring characteristic of scientific knowledge. The living world remains larger than the portion humanity has already documented. Hidden within the enduring reaches of the deep ocean, countless forms of life continue their ancient histories beyond ordinary sight, reminding us that exploration has never been a search for confirmation alone. It has always been an invitation to discover that the world still contains realities, waiting patiently beyond the edge of what is presently known. There are moments in natural history whose consequences continue unfolding long after the original event has disappeared beyond memory. Among those moments, few equal the passage from water onto land. The coelacanth stands beside that turning point, not as the traveler that completed the journey, but as the enduring companion of the lineage that did. Its broad, lobed fins, supported by sturdy internal bones rather than simple, flexible rays, remain among the clearest living reminders of a body plan that once approached an extraordinary possibility. Those paired fins move in an alternating diagonal rhythm, with the front fin upon one side advancing together with the rear fin upon the opposite side. Long before vertebrates walked across floodplains or forests, this pattern of coordinated movement had already begun to emerge beneath the sea. What appears today as the graceful motion of a deep water fish echoes a form of locomotion that would eventually become fundamental to life upon land. The significance extends far beyond anatomy. Earlier explorations of the coelacanth revealed regulatory genes associated with limb development that remain remarkably similar to those found throughout land vertebrates. Other regions of its genome preserve genetic instructions related to sensory systems that once carried importance near the boundary between water and air. These are not functioning blueprints preparing the coelacanth for life upon land. They are inherited records from an ancestral period when the evolutionary future of that broader lineage had not yet divided into separate destinies. Approximately 375 million years ago, one branch gradually entered environments where fins became capable of supporting weight against solid ground. Generation after generation, natural selection refined those structures into limbs. The descendants of that branch spread across riverbanks, wetlands, forests, deserts, mountains, and eventually every continent. Amphibians appeared first, followed by reptiles, birds, and mammals. Every familiar landscape occupied by large vertebrate life owes its existence to that remarkable transition from water to land. The coelacanth did not accompany that expansion. Its own lineage remained within the sea, continuing along a different path that led toward deep volcanic habitats rather than terrestrial ecosystems. Yet, remaining behind did not erase the older biological heritage it already possessed. Features inherited before the evolutionary separation continued to pass from one generation to the next, preserved because they remained compatible with life in its stable marine refuge. Seen from this perspective, the coelacanth becomes neither an unfinished experiment nor a primitive survivor. It represents a living reference point positioned close to one of evolution's greatest branching events. By comparing its anatomy and genome with those of lungfishes and modern land vertebrates, scientists can reconstruct with increasing confidence the characteristics shared before those ancient lineages diverged. Each comparison strengthens the understanding that the transition onto land emerged through gradual modification of structures that already existed beneath the sea. Watching a living coelacanth drift through deep water therefore offers something unusually direct. The alternating motion of its fins, the architecture hidden within those fins, and the inherited genetic framework carried within its cells together preserve authentic evidence from that distant evolutionary crossroads. This relationship is not symbolic, poetic, or imagined. It reflects a genuine biological continuity extending across roughly 400 million years of uninterrupted descent. Within the patient movement of that ancient fish rests a chapter shared by every amphibian, every reptile, every bird, every mammal, and every human being. The coelacanth chose no destination beyond its enduring marine home. Yet by remaining where its ancestors once lived, it continues to illuminate the forgotten threshold from which the living world above the waves first began its long walk across the earth. There are words in science that appear absolute until a single discovery reveals the limits hidden inside them. Among the most powerful is extinction. It seems to describe a final moment, the instant when the last living member of a species disappears forever. Yet the coelacanth transformed that familiar word from a certainty into something requiring patience, evidence, and humility before the immense scale of the natural world. In its practical scientific meaning, extinction is defined as the death of the final individual belonging to a species. The definition itself remains sound. The challenge lies elsewhere. No observer can witness every valley, every forest, every cave, or every depth of the sea at the same time. The conclusion, therefore, depends upon the reach of observation, and observation has always possessed boundaries beyond which knowledge becomes inference rather than direct experience. The coelacanth exposed those boundaries with extraordinary clarity. For tens of millions of years, no fossil younger than the ancient geological layers had been found. Natural history accepted that absence as evidence that the lineage had ended. Then a living individual emerged from waters where almost no scientific attention had previously reached. The fish had not returned from extinction. It had continued existing beyond the places where evidence had been sought. The mistake rested not within biology, but within the assumption that the available record represented the whole of reality. The deep ocean makes that lesson especially profound. Beneath approximately 200 meters, that is nearly 656 feet, conditions become increasingly difficult for exploration. Vast volcanic slopes, steep underwater cliffs, intricate cave systems, and immense stretches of open water remain only lightly surveyed even today. Human knowledge has expanded rapidly through improved cameras, remotely operated vehicles, crude submersibles, and advanced mapping technologies. Yet these achievements still illuminate only fragments of an environment covering most of the planet's living volume. That limitation does not invite fantasy. The overwhelming majority of species, judged extinct through careful fossil evidence, historical records, and exhaustive field surveys, truly have vanished. Entire branches of life's history ended without descendants, leaving only bones, impressions, or chemical traces preserved within stone. The coelacanth never overturned that broader understanding. Instead, it established that certainty must always reflect the quality and completeness of available evidence rather than confidence alone. This distinction carries profound consequences for conservation. When a rare species disappears from view for many years, researchers no longer ask only whether it has vanished. They also consider whether the remaining population could survive in places that have escaped meaningful observation. Search efforts become more deliberate. Habitat models become more sophisticated. Regions once dismissed as improbable refuges receive renewed attention because history has already demonstrated that remarkable survival can occur beyond ordinary expectations. The coelacanth therefore reshaped scientific method as much as scientific belief. It encouraged greater precision in the language surrounding disappearance and persistence. Instead of treating absence as identical to extinction, researchers increasingly distinguish between confirmed loss and incomplete detection. That careful distinction protects both intellectual honesty and practical decision-making, ensuring that conservation resources remain guided by evidence while acknowledging the unavoidable limits of present knowledge. In the end, the enduring lesson reaches beyond a single ancient fish. Every declaration about the living world exists within the boundaries of what humanity has been able to observe. Beyond those boundaries stretches an earth still containing remote depths, hidden landscapes, and biological histories that remain unwritten. The coelacanth offers neither misplaced optimism nor impossible promises. It simply reminds us that genuine certainty demands evidence equal to the scale of the question, and that the unknown remains larger than any map we have yet drawn. There is a tendency to imagine evolution as a staircase, each step carrying life towards something greater, more elaborate, or more intelligent than what came before. Within that picture, the coelacanth has often been placed upon a forgotten lower step, described as a living fossil that somehow failed to keep pace with the changing world. Yet, the fish resting within volcanic shelters beneath the sea tells a far more precise and remarkable story, one that dissolves the idea of evolution as progress and replaces it with something both simpler and more profound. Evolution has never possessed a destination. It does not strive toward perfection, complexity, or any final design. It is the gradual accumulation of change shaped by natural selection, responding only to the demands imposed by an environment. Every feature that persists does so because it continues to function well enough for survival and reproduction. When conditions change dramatically, organisms may change with them. When conditions remain comparatively stable across immense spans of time, far less alteration may be required. The world inhabited by the coelacanth offered exactly that unusual stability. Beneath the thermocline, among volcanic formations where darkness, temperature, and pressure changed only gradually over countless generations, the demands of existence remained strikingly consistent. The surrounding landscape beneath the sea certainly shifted as continents drifted apart, mountain ranges rose, and coastlines transformed. Yet the immediate conditions inside those deep refuges remained remarkably dependable. A body already suited to that environment encountered little pressure, demanding a fundamentally different design. This explains why the coelacanth appears so familiar beside its ancient fossil relatives. The resemblance does not reveal evolutionary failure. It reflects evolutionary success, measured by an entirely different standard. A structure that continues solving the same biological challenges need not be reinvented. Natural selection does not reward novelty for for its own sake. It rewards effectiveness, and effectiveness can sometimes look astonishingly unchanged across immense reaches of geological history. Across approximately 400 million years, continents assembled and separated, climates oscillated between warmth and ice, forests spread across newly formed landscapes, reptiles rose to dominance, birds filled the skies, mammals diversified, and human beings eventually appeared. During that same interval, 5 major mass extinctions transformed the composition of life on Earth. Entire ecosystems vanished, while countless evolutionary experiments reached their final chapter. Through all of that planetary upheaval, the coelacanth lineage continued occupying a niche that demanded remarkably little revision. This perspective also reshapes the meaning of adaptation. Adaptation is often imagined as acquiring something new, longer limbs, sharper senses, or more intricate behavior. Yet, adaptation can also mean preserving what already works. Stability itself becomes an evolutionary outcome when an organism remains closely matched to its surroundings. The absence of dramatic anatomical transformation may therefore represent not a lack of response, but the continuing confirmation that existing solutions remain effective generation after generation. The coelacanth embodies that principle with unusual clarity. Its lobed fins still provide graceful control through rugged underwater terrain. Its metabolism remains suited to a life unfolding at an unhurried pace. Its reproductive strategy, sensory systems, and body plan continue supporting survival within habitats that have changed comparatively little despite the restless history unfolding far above. Every surviving individual demonstrates that natural selection has repeatedly tested this design and found no compelling reason to replace it. Seen through that lens, the ancient fish drifting through its volcanic refuge ceases to resemble an abandoned experiment from another age. Instead, it becomes evidence that endurance may itself be among evolution's greatest achievements. Success is not measured by constant transformation alone. Sometimes, it is measured by discovering a form so precisely matched to its world that hundreds of millions of years pass. Oceans reshape themselves, civilizations emerge, and the essential design still answers every challenge that truly matters. On the morning of December 22nd, 1938, history turned upon a decision so ordinary that it could easily have unfolded another way. Marjorie Courtenay Latimer had almost chosen not to visit the docks that day. There were countless reasons to remain occupied elsewhere, countless small obligations that might have delayed the journey until the remarkable catch had already vanished into memory. Instead, she followed an instinct that seemed unremarkable at the time, walking toward a fishing vessel without knowing that one encounter would reshape humanity's understanding of life on Earth. Resting among the day's catch was a fish unlike anything she had seen before. It was not newly created by the sea, nor had it emerged from some hidden corner at that moment. It had belonged to a lineage that had endured while civilizations appeared and disappeared beyond the horizon. Long before the first cities rose from river valleys, before bronze was shaped into tools, before written language preserved the thoughts of kings and poets, ancestors of that animal were already moving through deep water with the same measured grace. Its lineage remained present through the rise of the Roman Empire, through the great voyages across unfamiliar oceans, through every generation whose stories survived in books, and through countless others whose names dissolved into time. It existed before the common ancestors shared by every living human being had taken their first breath. While continents continued their gradual drift and coastlines shifted almost beyond recognition, The coelacanth persisted beneath the waves, beyond ordinary notice, asking nothing from history except the chance to continue. Its future now depends upon circumstances very different from those that shaped its distant past. The great geological catastrophes that transformed entire continents failed to erase it. Mass extinctions passed overhead, while deep refuges softened their immediate effects. Yet fishing equipment reaching farther into deep water has introduced dangers that ancient evolutionary experience never prepared it to meet. Survival across immense spans of time offers no guarantee against pressures that emerge within only a few human generations. The deeper lesson extends beyond a single remarkable fish. The ocean is often imagined as empty because so much of it remains unseen. In truth, it contains layer upon layer of living history. Pressure, darkness, volcanic landscapes, and immense distance have preserved biological lineages carrying memories of worlds that vanished long before human beings learned to ask questions about their origins. Within living bodies, ancient chapters of Earth's history continue without announcing themselves to the surface. The coelacanth became the most recognizable of those chapters because chance finally carried one individual into human view. Once discovered, it was impossible to ignore. Yet the larger record continues beyond that encounter. There are underwater caverns no explorer has entered, volcanic slopes no camera has surveyed, and deep habitats where organisms continue their existence without witnesses. Many species remain unnamed, while others may already possess histories reaching far deeper into time than anyone presently suspects. The fish resting upon that dock was never a miracle suspended outside natural law. It was evidence that nature's story has always been larger than the portion humanity has managed to observe. Discovery did not create the coelacanth. Discovery merely aligned human attention with a reality that had continued uninterrupted through millions upon millions of years. As this journey reaches its final resting place, the enduring message belongs not only to one ancient survivor, but to the ocean itself. It remains older than memory, broader than certainty, and richer than every map drawn across its surface. Its greatest gift is not simply the creatures it reveals, but the enduring reminder that knowledge grows not by exhausting mystery, but by meeting it with patience, curiosity, and the willingness to look again where the world still keeps its oldest stories.